Hello friends, welcome to another lecture of EMT for BSc and MSc students. So here we are to discuss about the propagation of plane electromagnetic waves in an isotropic dielectric medium. That means non-conducting isotropic medium or isotropic dielectric medium, same thing. So that electric vector E, so magnetic field vector H are perpendicular to each other. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. Also let me know where are you from, okay, and in which college or university you study in the comment box, because I want to know about my audience. Okay, so if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. So we're gonna start with Maxwell equations. Let me write the Maxwell's equations first. So these are the Maxwell's equation, and let me write the meaning of these terms we're gonna use here, and let me mention here these are the meaning of this. So let me mention one more thing. So this is conductivity. Okay, so these are the Maxwell's equations. Now you see here, in case of isotropic dielectric medium, right? In case of isotropic dielectric medium, before that let me write few more relations. Those are here, you see, and this current current density J vector is conductivity into electric field vector, and this B vector is mu, then this is magnetic field vector H, then D is equal to, this vector is equal to epsilon E vector. Okay, let me write these relations as well. So in case of isotropic dielectric medium, you must know these things, that sigma is equal to 0 here, and rho, that is also 0, which is here in this case free charge density, and hence this J vector must be also 0. Okay, so if this is the case, then the above Maxwell's equations becomes of this form. So let me write here. Okay, just give me a second, let me write these things here. Okay, so now you see, then if we use these conditions, because we are considering isotropic isotropic dielectric medium, so in case of isotropic dielectric medium you must remember these conditions. Okay, and if you use these relations in this Maxwell's equations, then this Maxwell equations becomes Maxwell's equations in dielectric isotropic dielectric medium. So let me write here, for isotropic dielectric medium, the equation becomes here you see, in this case this thing's gonna be 0, right? This row, this one gonna be 0, and this remains same here, nothing to change, and that's why here you see that J gonna be 0 here, and let's see what we can change here. Okay, that's fine. So what we have got now, let me write here. So these are the Maxwell equations now for dielectric, isotropic dielectric medium. Let it be equation number 1, let it be equation number 2, and this is suppose equation number 3, and this is suppose 4. So what we have done here, this one you see, so this d here, you see this d can be replaced by epsilon vector e, right? So that's what we have done. This a becomes 0 now, right? Okay, so now you see, let me write those equations in the in the new slide. Okay, let me take a new slide. Okay, so these are the equations we have got now. Okay, so now what we're gonna take, we're gonna take curl of equation number 3. Okay, taking curl on equation number 3, taking curl of equation number 3 on both sides, then what we're gonna have, let me copy the equation number 3. Okay, so here is the equation number 3, then we're gonna take curl on both sides. So sorry, okay, so what we gonna do here, you see, if you take curl on the right hand side of this, then on the right hand side as well, then this, and we can write this here, you see, just give me a second. So we have taken curl on both sides, right? So that's what we have got. Okay, so hope you have understood this. Now you see what we are going to do in this case. So we're gonna use a vector identity, that is since we know that curl of a vector, suppose any vector A, is given by gradient of divergence of the vector minus Laplace operator than vector A. Okay, that's what we get. So using this property, this left hand side will be of this form, that this, instead of A, now we have electric field vector E. So what we can write on left hand side is, so let me replace this A by E vector. So here it is E vector now instead of A. So what we have done, we have applied this identity to this left hand side of this identity, right? Sorry, so left hand side becomes this, right? Hope you have understood this. So this is equal to this one according to this identity, right? So on the left hand side, on the right hand side, minus, so here you see del cross H. So here we can use equation number 4. So if you do that, then what you're gonna get, del t of, instead of writing del cross A, so we're gonna use this value. So then epsilon del E by del t, that's what we're gonna have, right? So now from here, what we can do, you see. Okay, now let's simplify this equation, right? You see, from equation number 1, if d dot e del dot d is equal to 0, then del dot e is also equal to 0, because we know that here you see the d vector is nothing but epsilon e. So if del dot d is equal to 0, then del dot e must be also equal to 0, right? Hope you have understood this. If that is the case, then what we can write, that from let me write this one here. Okay, okay. Now you see, next step after this, next step, let me write here. This part gonna be equal to 0 as del dot E is equal to 0. So that's why we're gonna left with we're gonna end up getting this sorry, this is E vector minus mu epsilon, then second order partial derivative of E with respect to t. That's what we're gonna have. So then you see, this equation implies Laplace operator E then minus mu epsilon this. So this is nothing but equation of wave, differential equation of wave, right? So we know the equation, this is in this form, you know, this is the equation of wave, this is in this form, right? Okay, so now you see, similarly we can show that similarly so let me take this as suppose equation number, and let me mention one more thing. So in this equation that here you can see, instead of this we have used this equation. Let me mention here, we have used equation number 4, so I haven't mentioned here, so it should be mentioned here. Okay, so just let me find some space here, just give me a second, okay. Okay, so using equation number 4, do mention this. Okay, okay. Now similarly what we can obtain that if we take curl on of equation number 4, then you're gonna get curl of, you know, del cross H, curl of del cross H, then is equal to, so epsilon del t, then curl of vector E. That's what we're gonna have. Okay, so now you see, curl of vector is this one. So if we use this equation number 3, and again if we use this identity, here as well, then it you know, then it gonna be equal to you know, divergence, grade of divergence of vector H minus Laplace operator E is equal to, sorry, not E, that should be H, that's supposed to be H. Okay, so H vector, then minus, so epsilon, sorry, not minus here, we don't need minus here. Okay, so epsilon del t, instead of E cross del cross E, we're gonna put this result, equation number 3, that's gonna be minus mu del H by del t. Okay, so here we have used equation number 3, using equation number 3. So then again you see, if we use equation number 2, then this part gonna be equal to 0. So here we're gonna get minus Laplace operator H, then minus mu epsilon, and second order derivative with respect to t of H vector. So here we're gonna write, since equation 2 gives that divergence of H is equal to 0. That's what we have got. So again, you know, this implies, so this is again the wave equation, if we see this A is equal to 0, right? So now let me give this is equation number so let me take this as equation number 5, so equation number 6. Okay, now let me copy equation number 5 and 6 and let me take a new slide. Okay, let me take a new slide. Okay, so here is the equation number 5, this is equation number 5. Okay, and here is the equation number 6. Let me copy this one as well, and this is equation number 6. So let me give it equation number 6. Now you see speed of EM wave it will be better if you write electromagnetic wave in exam. Okay, don't use short write the full form. Okay, wave in isotropic dielectric medium, that is V is equal to 1 by root over mu and epsilon. Now you see in free space electromagnetic wave travels with the speed of light, that is c, which is also equal to root over mu naught epsilon naught. So this is nothing but product of permeability and permittivity in free space, and that's now we are taking dielectric medium, right? So that's why instead of mu naught and E naught, we're gonna write mu and E in for the particular medium, and the velocity in that medium is V, that can be represented by V. So that's why this equation number 5 can be written this way, that equation number 5. So here you see this term can be replaced by 1 by V square, because if you simplify this, then V square gonna be equal to 1 by mu epsilon, which is gonna imply that mu epsilon is equal to 1 by V square, right? And similarly equation number 6, that's gonna imply this 1 by V square. So del second order derivative of h with respect to time t. So these are the EM wave equations in isotropic dielectric medium. Okay. Okay, now you see the solution of equations of this form. This is suppose equation number 7 and equation number 8, suppose. So equation 7 and equation number 8 are the EM wave equations in isotropic medium, and these equations are just give me a second. Solutions of equation number 7 and 8 respectively are given by let me copy this part and let me go to a new slide. Okay, sorry. Okay, now let me copy these things. Okay, so here you see okay, so the solutions are given by E vector. This is R is the position vector, right? E naught, it represents amplitude. E to the power I k vector, which is the propagation vector of wave, then minus omega t, and H vector that's going to be given by H naught, right? Okay, that's what we're going to have. Okay, so here this E naught and H naught are complex amplitudes. Amplitudes, constant in space-time, right? And this k vector is wave propagation constant. Right? Wave propagation constant. Wave propagation vector. Okay. Now let me take the equation number 3 and 4. So what were those? So here you see equation number 3 and equation number 4. Now let me copy these equations and let me go to the last slide again. So sorry, these are the equations. Okay. Just give me a second. Let me take a new slide. Okay, just wait. Let me take a new slide. Here are these are the equation number 3 and 4, and what are the solutions of EMF wave? Let me copy the solutions as well. So here you see these are the solutions of EM wave. Just let me write here properly. Okay, these are the solutions. Now you see, if we take the x component of this E vector, now if we take the x component of E vector, let me take x component of E vector. So just x component of vector E, that's gonna be, let me write it as Ex, and its amplitude E naught x e to the power I k dot, so let me write here kx now. So we are taking the x component of k into x minus omega t, because here you see this k vector that can be written as kx I cap plus ky j cap plus kz k cap, right? In vector form, and this r vector is nothing but x I cap plus y j cap plus z k cap, right? Z k cap. Okay, so that's why we can write the x component this way. Now if you differentiate with respect to x, then what we're gonna have, if you here e naught x, that's going to be constant, and if you differentiate this, then it's supposed to give you e to the power I kx x minus omega t. This function of function, then again you have to differentiate this, then we are differentiating with respect to x, so that's going to give you I kx. That's what we have got. So let me write the I kx first, and then let me write this one here. So here you see this is kx, okay, not k into x. So just give me a second. Okay, this is kx, not k into x. Okay, so don't be confused. Similarly, what we can do, before that, let me write it one more thing. This part is nothing but this one, right, which is equal to ex. So we can write I kx ex, right? So if you compare this, then you can write del x is equivalent to I kx. So therefore Therefore we can write del x is equivalent to ikx. Similarly, we can write del y is equivalent to iky, and del z is equivalent to ikz. That's what we can do. Right, now you see, so let me write here this symbol. Okay, now you see, if you differentiate this with respect to time t again, then what you're gonna get? If you differentiate this with respect to time t, then what you gonna have? So then you're gonna have del t ex. Then you see, differentiating this part, e to the power kx x minus omega t. If you differentiate this part within the bracket, so here this part gonna be 0 with respect to t, and here we're gonna get omega, and so here we have to write, as we have I here, so minus I omega. That's what we're gonna have. So this implies that del t, this operator, is nothing but, instead of this we can write minus I omega. Okay, right? So now you see, the del operator, this operator, which is nothing but you can see that del x I cap plus del y j cap and del z k cap, right? And this can be written, if we replace del x, del y, del z by these operators ikx, iky, sorry, it's okay, ikx, iky and ikz, then you see this will be of this form, right? Kx I cap plus ky j cap plus kz k cap, and which is nothing but the vector k. So sorry, here I forgot the I, so which is taken common, okay, because we have I with this every k. So here we're gonna get I, so we can write I k vector, right? So hope you have understood this. Now you see this equation number 3 and 4, right? If we replace this operator by I k vector, and if we replace this del t by this minus omega, I omega, then what we're gonna get? Then you see, then this equation number 3 becomes of this form. So equation number 3 and 4. So equation number 3 becomes of this form. You see, I k cross vector e. Okay, so let me write here, is equal to minus omega mu, then del t is minus I omega. So you can write here directly plus, okay, mu I omega vector h, right? Similarly, equation number 4 becomes of this form, k cross h, and that's gonna be equal to minus, one more thing, you can cancel the I, right, from both sides. You can drop I on both sides, then you can write e, you're gonna have k cross e vector mu omega h vector, and similarly equation 4 implies that k cross h is equal to minus epsilon omega e vector. That's what we have got. So now let me go to a new slide, copy these two equations. Let me copy these two equations. Okay, So these are the two equations. Now you see, from these two equations, it is clear that this magnetic field vector and electric field vector, right? So these two vectors, E and H vectors, are mutually perpendicular. Let me explain why. Okay. Not only these two, also this all the three vectors are perpendicular. Actually, E vector, H vector, and K vector. That means wave is propagating in the direction perpendicular to the direction of oscillation of E and H. These are all perpendicular, okay, mutually perpendicular, right? Let me explain why. Now you see, if we getting K cross E, that minus mu omega H, what does it mean? We know A cross B, if A cross B is equal to suppose C vector, that means this C vector is perpendicular to the plane containing A and B vector, right? Now again, if you see B cross C is A, that means this A vector must be perpendicular to the plane containing C and B, and this condition will be possible if these three vectors are mutually perpendicular to each other, right? This is A vector, suppose this is B vector, and this is suppose C vector. Now you see, C is perpendicular to the plane containing A and B. Similarly, A is perpendicular to the plane containing B and C, right? And so in this case, here you see, in this case also, if K cross E and K cross H gives this vectors H and E, so this three, K vector, then this E vector and B vector or H vector, this must be mutually perpendicular. So hope you have understood this. Okay, so thank you for watching. See you in the next video.